This will be the mathematical demonstration of partial and directional derivatives. So I consider this function that looks a nicer looking function. It's not exactly the same function we looked at in class, but it's the same idea. But I choose the same point here as a 2, 1, but the functions are slightly different. So t value will, if you move that one, you can see the point moves towards the right. So the first value here is showing the z value, so that z value there is a 3.01. As you move forward to the right, and you can see how the z value changes, it just decreases, and then it shows that down there the instantaneous rate of change of the z value there is -2. So it's decreasing, so as you go to the right, you can see the z value here decreases, and then instantaneous rate there is a -2. Next direction I'm showing here is a y direction. So if you move along here, and you can see it says that rate of change there is a 0, and it's because it's lined up nicely. So then that point, I think, it's vertically, it's tangent to one of those level curve that you don't see here. But suppose your point is here, you can see the vertical is happen to tangent to the level curve. If you stay on the level curve, the value doesn't change. That's why it's a 0. So that tangent direction is instantaneously, can't distinguish that you're changing the direction there or not. It's going to the same direction of the level curve. So those are the two partial derivatives. So, but eventually we're going to consider all the different directions like this. So if you're pointing to that direction like this, and then you can see if I increase, then rate of change is different. So I'm going to set this to 0 and mainly focus on not moving this point, so you know if you move along the rate of change is changing, but just moving the directions that I want you to look at, the rate of change. So if you look at that direction, then rate of change is 1.9. So if you move along to that direction, it's increasing. So let me move a little bit so that you know which direction we're going. So if you move around here, you can see somewhere around there is 1.9. If you go to that direction, then it's the best direction to increase, and this is the best direction to decrease. And if you go in between, and there's different rate of changes there. So by looking at this level curve, you kind of have a little bit of idea in as you move towards it, and how many different levels you're going through. That tells you kind of the rate of change there. So this will be the demonstration of a geometric interpretation of the partial derivative. So this is supposed to be like this, x coordinates. So this is 2, 1, and this plane is parallel to this xz plane. So you can see this xz plane there. So if you cut this graph of the function y equals f of x with this plane, this would be y equals 1 plane, so that it's parallel to xz. Then it leaves this intersection curve, and that's the curve you see right here over this xz plane. If you replace your formula f of xy with y equals 1, then you have this formula for x and z equals in the polynomial of x, that as we saw in class, this is a parabola. So let's change that to the other direction, and keeping it this direction. This is x, this is a plane x equals 2, the other one was y equals 1. So if you look around here, that's kind of parallel to yz plane. If you cut it like that, and it gives you this curve, and then the slope at that point right there is the partial derivative with respect to y, and the other one was a partial with respect to x. The slope of this tangent line for this curve in that plane is what's going on. So this is just the two planes, but if you change this one like this, as we swap around, and you can see the curve changes, these will be the directional derivative, and the meaning of this directional derivative will be the slope of each of these tangent lines. So as you swap around, you can see that slope of the tangent line changes as you move these things around like this. That's cool.